When we design memory for artificial intelligence, we tend to picture complex vector spaces or high-dimensional knowledge graphs. But in production environments, deployed agents remember data through a much older substrate, a basic file system. Look at Claude Code, Anthropic's memory tools, or standard skill libraries. They all maintain long-term memory the same way. They read, write, and reorganize simple markdown files nested inside directories using standard shell commands. Relying on this basic architecture requires engineers to make two untested assumptions. First, that a large language model can maintain a functional taxonomy as it scales, and second, that this organization yields a positive return on compute investment. A 2026 study by Zhao and colleagues provides the industry's first systematic stress test of these assumptions. By formalizing the chaotic reality of markdown-based memory, they isolated exactly what this architecture achieves. The data shows that actively managing an agent's memory taxonomy does not result in better answers. It buys search efficiency. Curating an agent's memory tree solves a unit economics problem, not an intelligence problem. This data shifts the engineering priority from improving model reasoning to managing the cost of retrieval. To measure this, the study defines the memory store formally as a rooted hierarchy of files. Every file is strictly operationalized as a triple: its specific path, a one-line text description, and the actual body content. Navigating this tree imposes a severe operational constraint. The agent is flying blind. To avoid massive compute costs, it makes top-down routing decisions using only the folder structures, the file names, and those one-line descriptions. Because the dense body content is locked out until a descent path is chosen, these short front matter labels serve as the sole routing signal. This blind routing constraint requires a strict definition of what a well-organized store actually is. The paper establishes a 5-part operational baseline, the taxonomy contract. Principle 1 is sibling distinction. Files sharing a parent folder must be perfectly distinguishable by their labels alone. If an agent has to open the file to know what's inside, the routing signal has failed. Principle 3 requires parent-child coverage. Exhausting a parent subtree must be conclusive. If the agent reads every file under a single branch, it can mathematically guarantee it has retrieved all relevant data on that topic. Without strict adherence to these operational principles, the file system ceases to be a memory structure. It degrades into an unnavigable text dump. To study how these text dumps form, the researchers separated the agent's workload into 3 distinct roles operating simultaneously over this single file store: management, search, and execution. The management agent carries the mandate to proactively integrate new chunks of data. It maintains the file structure by creating, merging, and splitting files as the data scales. The search agent operates in a strictly read-only capacity. It parses the taxonomy to answer queries and return cited evidence. Finally, the execution agent is the active operator. It takes the retrieved skills and context provided by the search agent and attempts procedural tasks in the environment. Between these agents and the raw file data sits the tool harness. This acts as a hard boundary layer, gating exactly which operations, like renaming or deleting, the agents are actually allowed to execute. Testing this 3-role architecture requires a specific methodological constraint to ensure the results are valid. This is the leak-free protocol. When the execution agent attempts a novel problem, marked here as task N, it is mathematically walled off from the current data stream. It is only allowed to query the memory store built during prior tasks. Imposing this quarantine isolates true transferable experience. It proves the agent is actually applying past lessons to novel problems, rather than simply regurgitating data from the current prompt. By isolating the 3 roles and enforcing this task quarantine, the architecture directly measures the specific value a memory store contributes to a model's success. When tested across all variables, the empirical data reveals a counterintuitive reality. No specific file structure wins answer correctness over a flat data dump. Let's run a comparison to see why. On the left is the organizer model, utilizing distinct categorized files. On the right is a verbatim dump, where all data is appended into one massive unformatted text file. When we track a query through the organizer, the search agent uses the routing tags to pinpoint and read exactly one targeted file. It processes roughly 120 characters, keeping compute costs minimal. Running the exact same query through the verbatim dump yields a very different operational load. Without any routing signals, the agent is forced to blindly ingest the entire massive file. Token usage spikes. But look at the output. Both the organizer and the dump extract the correct answer. The standard QA evaluations driving the industry are shape-blind. They reward the final accuracy of the answer, but they ignore the computational brute force required to retrieve it. A sufficiently powerful search agent does not gain capacity from a well-organized file tree. If the model is strong enough, it will eventually find the fact in a chaotic text dump. It simply uses the organized taxonomy to save time. The measurable benefit of curated memory is search economy. As the volume of material scales up, a structured taxonomy functionally halves token retrieval costs. Spending compute on a management agent to organize files doesn't make the downstream execution agent smarter. It operates purely as a cost control mechanism for retrieval economics. But running a management agent over multiple continuous sessions introduces a severe physical threat to the taxonomy itself. This chart tracks taxonomy adherence against store growth. For all but the most computationally expensive LLMs, strict adherence to the file structure actively degrades as new data accumulates. This downward slope is driven by a specific degenerative algorithmic behavior, silent condensing. Silent condensing occurs when a management agent attempts to optimize its store. It lazily rewrites multiple distinct, well-labeled subject files and collapses them into a single, generic junk drawer file. This lazy merge permanently destroys the sibling distinction and parent-child coverage principles we established earlier. The navigational metadata is gone. Silent condensing is mathematically worse than a raw text dump. A text dump is obviously flat. A condensed file falsely appears organized, hiding the fact that it has stripped out the very signals needed for efficient routing. The greatest risk in deploying file system memory is not a failure to organize. The risk is allowing an unconstrained LLM to organize the data badly, actively deleting its own capacity to navigate. Mitigating that risk requires adjusting an architectural lever that developers often overlook, the tool harness. The study measured how these constraints affect the store. Because an agent's policy is bound to the operations it can actually perform, modifying the harness, like revoking permissions to split or rename files, reshapes the memory tree as much as swapping the model itself. No matter how smart the model is, it cannot maintain a taxonomy if the harness denies it the necessary tools. An agent's memory curation policy is strictly bound by the action space its tool harness enables. To maintain integrity over time, developers must write strict preservation rules into the harness to block silent condensing outright, optimizing the memory architecture strictly for search economy rather than benchmark correctness. The Zhao study formalizes these mechanics perfectly within a single conversation horizon, but maintaining the structural integrity of an LLM-managed file system over multi-month deployments remains an unsolved frontier for the industry.